Okay, in this video, I want to discuss arguments and the mathematical structure of arguments. Now, the main focus here is the validity, or determining whether or not an argument is valid or not. Okay, so a few things we want to touch on in this video, identifying the difference between a valid argument and a fallacy. So an invalid argument we'll call a fallacy. And the way we're going to mathematically prove whether or not an argument is valid is using truth tables. And we'll talk about some common types of fallacies and some common types of valid arguments, and we'll go from there. So a logical argument consists of two parts. It's this set of premises, or the things that on which the conclusion is based, and then there's the conclusion. And so premises are statements, and we've defined statements already. So premises are statements that are offered as like supporting evidence. So our goal here is, given an argument, or basically, so an argument, again, argument is a set of premises and a conclusion. Now our goal is to determine whether or not an argument is valid or not. So we'll say an argument is valid, and this is the definition of a valid argument. An argument is valid if the conclusion absolutely has to follow from the set of premises. If not, we call it an invalid argument or a fallacy. Okay. Now, what's important to note here is that we're not talking about truth or falsehood. We're not talking about true or false. We're talking about valid or invalid. So we're talking about the structure of the arguments. Okay, so we need one definition before we look at an example, and that is a tautology. So a tautology is basically, it's a statement, a compound statement that is always true. Or basically, if you take a compound statement and you analyze the truth table, you get all true. So in any case, the statement is true. Okay, now we don't need to dip too deep into this idea of a tautology. All we really need to know is tautology means always true. That's it, and that's the key. All right, so now let's look at an example. So here's an example of an argument. So we have two premises, and we have a conclusion. Premise number one is a conditional statement. If it is sunny, then I go to the beach. Premise number two, I'm at the beach today. The conclusion is it is sunny. All right, so based on these two premises, assuming that these two premises happen, does it necessarily follow that the conclusion happens? All right, so before we do this, let's look at like how we go about testing. So remember, the whole point of this is to determine whether or not an argument is valid. So this is the question: valid or invalid. So this is the question we're trying to ask, or this is the question we're trying to answer. Now, we'll come right back to this argument, but let's talk about how we go about doing this, how we go about testing whether or not an argument is valid or not. Okay, so the first thing we do is we rewrite the argument using mathematical logic symbols, so like P's and Q's, conjunctions, disjunctions, negations, conditionals, and so on. All right, so we'll write the argument as a conditional statement. So it's like basically do the premises imply the conclusion? So here's the conditional. Now, normally we use this symbol, a single arrow, for the conditional. In the context of arguments, we normally use a double arrow. It's just a different notation, but it means the same thing. So the double arrow and the single arrow, they both mean conditional. And then we'll set up a truth table. So we have to, so once we write the argument in symbols, Then we'll set up a truth table for that argument, and if it is a tautology, meaning all trues, all t's, then the argument is valid. Okay, so let's apply this approach. Write the argument symbolically as a conditional statement, set up a truth table, and determine if it's a tautology. Let's apply this to the previous example. Premise number 1, if it is sunny, then I go to the beach. Premise number 2, I am at the beach. Conclusion, it must be sunny. Okay. So let's think about this. Let's think about this argument sort of informally, not using any form of mathematical notation. So based on these two premises, can I be at the beach on cloudy days? Does the fact that I'm at the beach mean it must be sunny? I don't know. Is premise 1, that's if it is sunny, then I go to the beach, is that the same as saying I only go to the beach if it is sunny? Do these two statements mean the same thing? Interesting. Okay, so let's test this. So if we're using the approach we talked about on the previous slide, step 1, write the argument using symbolic mathematical logic. Okay, so we have two statements. It is sunny and I go to the beach. Okay, so those are our two simple statements. So the argument looks like this. Premise number 1. So that's this. So let's switch it up. And premise number 2. So if premise number 1 and premise number 2, do they imply the conclusion? And here's the conclusion. So premise number 1 and premise number 2 imply the conclusion, which is it is sunny. So here's our conclusion. All right, so let's set this argument up as a truth table. So we have if it is sunny, then I go to the beach. I am at the beach, therefore it is sunny. So these three little dots, this means therefore. Okay, so in our argument that we set up on the previous slide, we have three logical connectives. We have the conditional, we have a conjunction, and we have another conditional. So three logical operators, three steps to putting together our truth table. All right, so step 1, the conditional. So we'll work inside out. So in the inner parentheses first. So we'll do the conditional, the inner conditional first, then we'll do the conjunction, and then we'll do the conditional on the outside. So definition of the conditional statement. The conditional statement is only false when P is true and Q is false. So we covered these definitions on a previous video. So again, we're just applying the definitions of and, or, not, and if then. Conditional, negation, conjunction, disjunction. All right, so our truth values for the conditional are true, false, true, and true. All right, so now we'll move on to the conjunction, the next one. So now an and statement is only true if both statements are true. So for this conjunction, we're looking at this column, the P implies Q, and we're looking at the Q column. Ooh. We're looking at the P implies Q column and the Q column, and we're connecting these two columns with a conjunction, with an AND. So the only time a conjunction is true is if both statements are true. So true and true equals true, false and false equals false, true and true equals true, and false and true equals false. Okay, so again, this is the final answer over here. So we're basically this is our sort of scrap work on the way to coming up with the overall final truth values of the entire statement. Okay, so now we have the first conditional done, we have the conjunction done. So now the second conditional. So we're combining this column, which is here, and this column, which is here, with a conditional. And this, the P implies Q and Q, that comes first. So true implies true, that equals true. False implies true equals true. Oh, but true implies false. That's false. And false implies false. That's true. But because we didn't get 4 truths, we've just shown that this argument is invalid. The only way an argument is valid is if that the overall truth values are all true. In this case, one of them is false. So this argument is not valid. Okay, now we'll come back here in a sec. So let's go back to the original argument. If it is sunny, then I go to the beach. That means every sunny day I'm at the beach. Every sunny day I'm at the beach. Okay, so if the day is sunny, I'm at the beach, but that does not imply the opposite. That does not imply if I'm at the beach, it is a sunny day. So if I could go to the beach every single sunny day, I could also go to the beach if it's cloudy or if it's raining. Okay, so we've just shown that this argument is not valid. All right. So there's a specific name for this type of argument, which takes this form. P implies Q and Q imply P. This is called fallacy of the converse. Another example, almost identical to the one we just did. If it's Friday, then I'll go to happy hour. And today I'm at happy hour. Therefore, it must be Friday. Well, that's not necessarily true. I could go to happy hour on a Tuesday as well. All this is, what the premises are saying is that every single Friday I'm at happy hour. That doesn't prevent me from going to happy hour on another day of the week. Okay, so this is an example of fallacy of the converse. All right, there's another common form of an invalid argument, and that's called fallacy of the inverse. So if I exercise every day, then I will lose weight. Okay, so let's looking at this. If I exercise every day, then I will lose weight. Does that mean that the only way to lose weight is to exercise every day? No. I mean, I could stop eating and I'll lose weight. So if I exercise every day, then I will lose weight. I don't exercise every day. So here is your I exercise every day. That's your P. I will lose weight. That's your Q. So the fallacy of the inverse is if P then Q, or P implies Q. If I exercise every day, then I will lose weight. And not P. I don't exercise every day. Therefore, not Q. I won't lose weight. Well, that's not a valid argument because, again, like I said, there are other ways to lose weight. All right, so here's a couple of examples of common types of logical fallacies. Now let's look at some valid arguments. So one, the law of detachment. P implies Q, or so if our premises are if P then Q and P. So if our team wins on Saturday, so our team wins on Saturday is the P, then they go to a bowl game. That's our Q. And our team won Saturday. So we have if P then Q and P. Those are our premises. Then our team goes to a bowl game. Implies Q. Okay, so there's our law of detachment written symbolically. Conclusion. Okay, so here are our premises, and Q is the conclusion. So this is a form of a valid argument. If you set up a truth table for this, the final column, when you're done the truth tables, the overall truth values will be all true. Okay. The law of contraposition. P implies Q and Q. Therefore, P. So you see the law of detachment and the law of contraposition, just the P and the Q are switched. In the law of detachment, P is a premise and Q is the conclusion. And if Q is the premise and P is the conclusion, we call it the law of contraposition. So here's an example. If I try hard, then I'll get an A. So we have premise P implies Q. And the other premise is I didn't get an A. Oh, this should be a not Q. I didn't get an A. So P implies Q and not Q. Implies I didn't try hard. And so our conclusion is P. Okay, so this is based on the definition of what's called the contrapositive of a conditional. So if a conditional statement is if P then Q, the contrapositive, which is an equivalent statement, is if not Q, then not P. Okay, so that's the premise, or that's the sort of justification behind the law of contraposition. Okay, we have the law of syllogism. If I make an illegal U-turn, so we'll call that P, then I'll get a ticket. We'll call that Q. And the second conditional, if I get a ticket, which is the Q, then I'll get points on my driving record. And so that's the R. So we have the premises, if P then Q, and if Q then R. Therefore, so if P implies Q and Q implies R, then what this rule is saying is that P must imply R. P implies R. Okay, so that's the law of syllogism. And the last one I want to mention is the law of disjunctive syllogism. And my top client demands the penthouse or an executive suite. Oh, this looks wrong. Sorry, let's switch this up. Let's switch this up. My top client demands the penthouse or an executive suite. And he couldn't stay in the penthouse. So if penthouse is P and executive suite is Q, so P or Q, and he couldn't stay in the penthouse. So that's not P. Therefore, Q. So P or Q must be true. If P is not true, then Q must be true. So he demands either the penthouse or the executive suite. He couldn't stay in the penthouse, therefore he stayed in the executive suite. This is an example of the law of disjunctive syllogism. Okay, so that's it for this set of notes. In the next video, we'll go through some specific examples using truth tables to test whether or not arguments are valid.